Howdy guys, so this is the start of our brand new topic, which is vectors in the plane, and this video here is just going to be an introduction to the beginning of vectors. So suppose that you are asked, where is your school in relation to your house? It is not enough to give an answer such as 4 kilometres. You need to specify a direction as well as a distance. You could give the answer 4 kilometres northeast. So the fact that you've added this northeast aspect here gives it a direction as well as a distance, and hence it's a vector. So position is an example of a vector quantity. Now, if anyone's doing physics, you've probably spoken about this a little bit in regards to vectors. If you're not doing physics, that's okay. This will be absolutely fine. So now we're quickly going to just talk about directed line segments. So a quantity that has a direction as well as a magnitude can be represented by an arrow. The arrow points in the direction of the action. The length of the arrow gives the magnitude of the quantity in terms of a suitably chosen unit, and this will make sense more as we go along. So arrows with the same length and direction are regarded as equivalent. These arrows are directed line segments, and the sets of equivalent segments are called vectors. The directed line segments shown all have the same length and direction, and so are equivalent, so they're talking about these ones here. The directed line segment from point A to point B is denoted by AB with that arrow on top. For simplicity of the language, this is also called vector AB. That is, the set of equivalent segments can be named through one member of the set. The 5 directed line segments in the diagram all name the same vector because they can all be equal to AB. So what I'd suggest writing down, I think if you want to take some notes, is really just this section. I don't think you need too much more than that. Column vectors. So we haven't looked at chapter 16 yet, but don't stress. So if we look here, so to make a column vector, so for example, the column is 3, 2, corresponds to the directed line segments, which go 3 across and 2 up. So you go across and then up. So see, A and B is the vector, but it's going 3 across and 2 up. So you get this column vector here of 3, 2. So just a little bit quickly on vector notation. So vector is often denoted by a single bold lowercase letter. The vector from A to B can be denoted by AB with an arrow or by a single letter V in this case. That is, V is equal to that. Obviously we can't write in bold, so another way it can be written is when a vector is handwritten, the notation is this. To be honest though, I'd stick with this notation. I think it's the easiest to understand. It's also the easiest to write. However, just be aware that within questions you might see it in those other ways. Alright, so here's an example where it wants us to draw a directed line segment corresponding to the column vector 3, negative 2. So if we think about what we were talking about before, the 3 means that we go across to the right by 3, and the negative 2 means we go down by 2. Now obviously we can then figure out where we start, but what I'm going to do is just quickly take a photo of the example because it's going to be much neater than mine. Now this is just one possible solution. It could be anything, but if we have a look at these coordinate points here, so at A we've got 1, 1, and then at B we've got 4, negative 1. So as you can see now, it's gone across to the right by 3 because it's gone from 1 to 4, and it's gone down by 2 because it's gone from 1 to negative 1. But you could have started it at any point if you were doing this example. You just need a directed line segment that goes 3 across and 2 down. Alright, so here's our next example. So the vector u is defined by the directed line segment from 2 to 6. Oh, sorry, I moved that instead of drawing. So 2 to 6 to 3 to 1. Find u where we've got A and B. So obviously we're starting at 2 and we're ending at 3. So remember the first number when you're looking at this, so u is equal to, now the first one is across. So we're going from 2 to 3, so that's going to be 1. And then the next one is how far down or up we're going. So in the vertical plane. So if we're looking at 6, to go to 1, we're going with negative 5. So then really we can say that A is equal to 1 and B is equal to -5. I hope that makes sense. If not, just make sure you let me know and we can have a bit more of a chat about it. Okay, now we're looking at addition of vectors. Again, if you're doing physics, you've probably come across this already, providing you're doing that topic. If not, that's okay. So if we've got two vectors u and v, can be added geometrically by drawing a line segment representing u from A to B, and then a line segment representing v from B to C. So we've got u here and v here. The sum of them when you add them together is the vector from A to C. So from this point to this point, as you can see, is u plus v. The same result is achieved if the order is reversed. That is represented in the diagram on the right. So if you can imagine here, we're going A to D and then D to C, but that will still give us AC. Okay. The cool thing is vectors can be also added together using their column vectors. So the two vectors can be added, as I just said, using column vector notation. For example, if u is 4, 1, so it's going 4 across and 1 up, and v is -1, 3, that means it's going -1 this way and 3 up. If we add these, so see we have, we've got 4 and -1 gives us 3, and 1 and 3 gives us 4. That means if we're talking about uv, it's going to go across 3, which we can see here, and up 4. So up 4. So you can also add the columns to find what the resultant vector would be. Now we're going to look at scalar multiplication. So multiplication by a real number, or a scalar in this case, that's what they're calling like a real number, changes the length of the vector. For example, 2u is twice the length of u, and half u is half the length of u. So if you have a look here, we've got u, you've got 2u and half u. So I hope that should make sense. So we have 2u, which is u plus u, and half u plus a half u will give you u, basically. I think that's all pretty stock standard maths there. In general, for k within R, so R here means all real numbers. So what they're saying there is if you've got k within all real numbers, the vector ku has the same direction as u, but the length is multiplied by a factor of k. And this plus means that it needs to be positive, because if it was negative, the direction would actually change. And I'm sure that's what they're going to talk about next. So k could be any number, providing it is positive, and that means the vector will go in the same direction, but it will be a multiple of what it is. So when the vector is multiplied by -2 in this case, the vector's direction is reversed and the length is doubled. So see how the arrows here, or the arrow here is going a different direction to this one. That's because the direction changes because of the negative, but it is still twice the length. When a vector is multiplied by -1, the vector's direction is reversed, but the length remains the same. So if we look at u here, the negative u is -3, -2. 2u is 6, 4. -2u is -6, -4. All you're doing is multiplying that scalar into the column vector. If u is equal to AB, then -u is equal to -AB, which is then equal to BA. Because if you think about, if you've got A, B, like this, so that's your vector. If you've got, and we're saying that's u, -u will then be this way, BA. So you could write -AB, but then what we'll use as better notation is BA, because the vector is now going from B to A. The zero vector is a nice easy one. The zero vector is denoted by 0 and represents a line segment of 0 length. So really it almost doesn't exist, or it doesn't exist. The zero vector has no direction. Something that might come up, but basically zero vector just doesn't really exist. It has no direction, and the line segment is 0 length. Also, if we're talking about subtraction of vectors, so to find u minus v, we add -v to u. So if we've got u here and v, so u will go the same way as it has, but then the v will change direction. So instead of adding the v on like this, as it normally would, we draw it in the other direction, or we attach it the other way, and then u minus v is this way. If we had it out this way, this would be u plus v. Okay, hopefully that makes sense. All right, so for the vectors u and v, find 2u plus 3v. So if we look at what 2u is, so 2u is going to be 6, negative 2. We're just timesing it by 2. And 3v is going to be equal to, what do we got there? Negative 6 and 6. So really, probably an even better way of writing it out is we could add 2u plus 3v is equal to 2 lots of 3, negative 1, plus 3 lots of negative 2, 2. And we know that, as we've already found these, plus negative 6, 6. So that's going to give us 0, 4. So what that means is this vector here is going to go across 0 and up 4. So I hope that makes sense on how to do that one. Alright, last concept in this video, I promise, because I know there's lots that's been in here. So for two vectors AB and BC, we have AB plus BC is equal to AC, which we've done before. So this is polygons of vectors, because obviously this then makes a triangle. For a polygon ABCDEF, we have AB to BC plus CD plus DE plus EF plus FA equals 0. And the reason they've got it equal to 0 is because it ends up at the same point. So if we think about AB and we go all the way around, they're going to say that it's equal to 0. And last example for the video. So illustrate the vector sum AB plus BC plus CD, where A, B, C are points in a plane. So say we've got A, we've got B, we've got C, and we've got D. So A, B, C, D. All we need to do is connect AB with an arrow going to B, because it's AB, BC, CD, and remember so it's asking for the vector sum. So the vector sum means that we need to connect it back together. So it'll be like that, but you can obviously draw it all in the same color. Actually, I lie. It should go this way. And it should go that way because the vector sum is going A to B, B to C, C to D. Therefore, our vector sum is A to D. So don't get caught up in just following the pattern like I just did and going the arrows the same way. Because we're going around here, our vector sum goes from A to D, so we need to have it this direction. Alrighty, and these are the questions that you'll do in class on Thursday. So there's a few there, but lots of them are nice and simple. And then there'll be some more videos ready for week 7. Can you believe it? We're already almost in week 7. Crazy. Thanks, guys.